Ammonium fluoride, you have ammonium ions and chloride ions. I don't care about the chloride ions. I do care about the ammonium ions. Ammonium ions is the conjugate acid of ammonia. So I have a solution basically of conjugate base and acid. Okay, I have the conjugate acid-base pair. I have a weak acid, which is this ammonium ion, and its conjugate base. And what could come right to mind with that? Well, if you have weak acid and conjugate base, you can use the Henderson-Hesselbach equation. That's the only time you can use it, if you like using it. Otherwise, you can set up the X table. Either way, you get the same answer. So it's what we call a buffer solution, and we'll talk a little bit more about that again later. But that's the criteria of these buffer solutions if you use the Henderson-Hesselbach equation. That's how I did it here. Notice, so I need to determine pKa. pKa basically is minus log base 10 of the Ka value. Ka is given in this problem. Actually Ka wasn't given. Kb was given for the base. Now I'm going to talk more about this later. But anyway, to use the Henderson-Hesselbach equation, pH equals pKa plus log of the ratio of the base over the acid. That's always the case, and that ratio could be moles or concentrations. Take your pick, whatever's easier. Now, the little bit of mishap here, issue is that you're not given the pKa value, but you're given is Kb. Now, we'll talk more about this a little bit later. Ka and Kb are always interrelated because Ka times Kb equals Kw, which is the autoionization of water. I'll show why that is later. But it means that whenever you're given Ka, you can calculate Kb, and vice versa, whenever you're given Kb, you can calculate Ka. The product of the two always equals the autoionization of water, which at room temperature is 1 times 10 to the minus 14. So with this sort of expression, we can convert to Ka given the Kb, and we get a number of like 5.6 times 10 minus 10. So this ammonium ion, NH4 plus, okay, is a very weak acid. Is a Ka value of 10 minus 10. Okay, so pKa, P of anything is always minus log base 10. So pKa is minus log base 10 of Ka. Okay, so you take that, and that's 9.25. Now plug that into the Henderson-Hesselbach equation. So you have pH equals 9.25. Whoops, let's move it this way a little bit. Plus this ratio log term, which is 0.097. And we get 9.35. Notice that since the ratio here, you had a little bit more base than acid, the log term was positive, okay, which means it brought the pH up from pKa, and so with a little bit more base than acid for this buffer solution, the pH is going to be a little bit higher than your pKa point. If the two are equal concentrations of weak acid conjugate base, you have a ratio, you have log of a number, log 10 of ratio of 1, and log 10 of any of 1 is equal to 0. Okay, any log of 1 is equal to 0, by the way. And that's what we have. So basically a little bit more base than acid. You have a positive term for the log term, slightly positive because you have slightly a little bit more base. And you have a little bit higher type pH, which means it makes sense, a little bit more basic than from the pKa value. Okay, now that's with the Henderson-Hesselbach equation. And I thought here, let's see if I did this. Yes, I can show very quickly, I'm not going to go in detail here, but you could also do it with the ice table. This just shows that it can be done, and I'll put it on Blackboard later. I'm not sure I have enough time to go through in detail. But to do the ice table here, okay, oops, let's see if I'm doing this. No, I'm going to skip over that. Okay, that's a different problem. Okay, so I'm going to hold off on that, and I'm going to switch to the next problem. But the questions on that?
Can you clarify when you use KB? That was a little bit confusing.
When you use KB? Okay, you can use KB if you're dealing with weak base plus water as your solution. So if you have a solution of just weak base and water, you can set up your ice table with KB. An example of that is where I did 0.25 ammonia. That was actually last lecture. I did 0.25 molar ammonia in water. I used KB with the ice table. Okay? If you use the Henderson-Hesselbach equation, I would recommend that you just always work with Ka, because that's how this Henderson-Hesselbach equation works with Ka. And there's a lot of underlying issues I don't want to confuse you about, but I could just say that it'll work for you. Okay? And so basically so we have a weak base in water, use KB. If you have weak acid and conjugate base, you have a buffer solution. I recommend you using Ka, just to keep it simple. I always use Ka. Okay? And what other cases we have? I think that's about it. So to answer the question, when you use KB, basically when you have weak base in water. Okay? In this case, we had weak base and conjugate base, conjugate acid. So it's a buffer solution, which means you either use the Henderson-Hesselbach equation here, or you could set up a ice table with the Ka expression, and that would work as well. I don't think I did that here. No. But I'll show with the next problem how we can do it the other way. Okay? Any other questions? No? Question? Yeah. What's that? A weak base, yes. I need to use a weak base. Yes. When you do an ice table, well, when you have just ammonia and water, yeah, you have OH minus. Now, if you have ammonia and ammonium ion, you have both. And the truth of the story is you can work with the reaction as Ka or Kb. So you can write the reaction either way and set up your expression how you write. You can write ammonia and water going to ammonium ion and hydroxide, or you can write ammonium ion plus water goes to ammonia and hydronium ion. Okay? And however you write that reaction, you use the corresponding Ka or Kb. And you can do it both ways, you'll get the same answer. Because in the end, we're going to use this double small x approximation. And because of that, it'll work out, numerically you'll get the right answer. I suggest how to keep things simple is always work with a Ka equilibrium. The only time you can't use Ka really is when you have weak base in water. Because there's no weak base to start with, weak acid to start with. Okay? So I'm trying to keep things simple here, as simple as I can, and kind of glossing over some